In this lecture, we'll see how linear transformations on a vector space can be represented in the form of a matrix when a particular basis is given. Okay, and we'll particularly see this for real vector spaces. So consider a vector space V over a field F. Let A be a linear transformation on the vector space V. So from the definition of linear transformation, we know that for all vectors in the vector space, you get a vector in the same vector space due to the action of this linear transform on the vector x. Also, we know that this linear relationship holds for all pairs of vectors in the vector space and for all pairs of scalars from the field. This is what we know. Now, we also know that there is a basis which is associated with the vector space. What we are interested in how the matrix form of A will be with respect to the basis x. Okay, we will be considering only real vector spaces on finite dimensional vector spaces. For this discussion, we will consider finite dimensional real vector spaces. Okay, now let the basis that we are considering have n number of vectors in it, as we are considering the dimension of this vector space to be n. Okay, now if A acts, as we saw, if A acts on a vector from the vector space, it comes to lie in the same vector space V. So this vector can also be represented as a linear combination of the basis vectors x1 till xn. So let me write it as this, where xi's belong to the basis and beta i's are from the field for all I. Right. Now I need to hence, so basically what is happening is, if I know, or rather let me put it down like this. So y can be represented as a linear combination of this. Similarly, x can also be represented as a linear combination of the basis vectors. Let me label them as this. So when I say y is equal to ax, which is equal to A acting on the linear combination of the basis vectors, is same as considering this, okay. So if I know how all the basis vectors are being transformed, well, I'll be able to somehow comment on some relationship between beta I, gamma I, and how the matrix of A is going to look like. Okay. So let's see how A transforms each of the basis vectors. So consider the vector from the basis. When A acts on the basis vector, it results in a vector in the same vector space. So Axj can also be expressed as a linear combination of the basis vector. So I can express it as I equal to 1 to n alpha ij xi, where alpha ij belongs to the field for all I equal to 1 to n and the j that you have considered. This can also be represented as the following. This is alpha 1j, alpha 2j, similarly alpha nj. Okay, so this is how it is represented. Now, so what you have is for a x1, you will have x1 x2 till xn multiplied by alpha 1j, alpha 1 1 2 1 alpha n1. Similarly for a x2, you will have x1 x2 till xn multiplied by alpha 1 to alpha 2 to till alpha n2, and if you keep on doing so on, axn is nothing but x1 x2 xn multiplied by alpha 1n alpha 2n till alpha nn. So if we put them all together, what I essentially have is A acting on x1 x2 xn is essentially a x1 a x2 a xn, and this is same as x1 x2 xn multiplied by alpha 1 1 alpha 2 1 alpha n1, similarly alpha 1 2 alpha 2 2 till alpha n2, and alpha 1n alpha 2n alpha n. So this is what you have. Okay, so this matrix here that you see, which is circled in red color, is the matrix representation of A with respect to the basis X. This is the matrix representation of A with respect to the basis X. Okay, so what you see here carefully is when A acts on x1 and gives you a vector, we represent that vector as a linear combination of the basis vectors. So the coefficients or the scalars associated in this linear combination, due to the vector received because of the operation of A on x1. So if you see the structure of this matrix representation that we have got and compare it with what we have got for ax1, ax2, axn, we'll see some nice structures. So what is that? When A acts on x1, it gives me a vector in the vector space itself. So I can express ax1 as a linear combination of the basis vectors. So the coefficients that are associated with this linear combination, if you see, they form the first column of the matrix representation for A. Similarly, when A acts on the second basis vector, it gives us a vector in vector space, so I can express it as a linear combination of the basis vectors, and hence the scalars or the coefficients associated in this linear combination form the second column in the matrix representation of the transformation A. Okay, so basically what is happening is when A is acting on the jth basis vector, the the vector that comes out can be expressed as a linear combination of the basis vectors, and hence the coefficients or the scalars associated in this linear combination form the jth column of the matrix representation that we have for the A. Okay, so this red circled one is the matrix representation of A with respect to basis X. Please remember that we are doing this when the field associated is reals. Okay, we are considering only real vector spaces. So let's see some examples of this matrix representation. So the first matrix representation that we will consider is for the linear transform when the vector space is of second order polynomials or second degree polynomials over the field reals, and the linear transform is the derivative operation. Let us represent this derivative operation by D. We'll find the matrix representation for this derivative operation for the basis 1, t and t square. So what we are trying to do is to find the matrix representation of the derivative operation with respect to the basis x. Okay, so when derivative operator acts on the vector represented by 1, what we get is 0. This is 0 times 1, 0 times t plus 0 times t square. This is the linear combination. Similarly, when d acts on t, we get 1, which is 1 times 1, 0 times t and 0 times t square. D acting on t square gives me 2t, which is 0 times 1 plus 2 times t plus 0 times t square. Okay, so from here what do we get? The derivative operation with respect to the basis x is, the first column is the coefficients arising in here, which is 0, 0, 0. The second column is the coefficients arising here, which is 1, 0, 0. And the third column is because of the coefficients arising here, and it is 0, 2, 0. So this is the representation of the derivative operation with respect to the basis x. Now let's say that I consider another basis, which is 1, t, and let's say 1 minus t square. Okay, so this is another basis. What would the matrix representation of D with respect to this basis Y looks like? So D acting on 1 gives me what? 0, which is nothing but 0 times 1, 0 times t, and 0 times 1 minus t square. Similarly, D acting on t gives me 1, which is 1 times 1, 0 times t plus 0 times 1 minus t square. And D acting on 1 minus t square gives me minus 2t, which is 0 times 1 minus 2 times t and 0 times 1 minus t square. So the matrix representation of the derivative operation with respect to the basis y is 0, 0, 0, the coefficient corresponding to the first operation on first basis vector. Then you have 1, 0, 0, coefficients corresponding to the operation on the second basis vector, and 0, minus 2, and 0, coefficients corresponding to the operation of derivative operator on the second basis vector. Now if you compare this matrix representation and this matrix representation, they are different because the underlying basis is different. So for a given basis, the matrix representation of the linear transformation is unique, but if the basis changes, of course the matrix representation may or may not change. Okay, so in general they may not be same. And let us consider another vector space, which is basically the set of real matrices, and the field is real, so we are considering 2 cross 2 real matrices. The linear transformation that we are considering is the transpose operation, which will denote by, let's say, A. The basis that we are considering in this example is 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So this is the vector x1, vector x2, vector x3, vector x4. So when A acts on x1, I get 1, 0, 0, 0, which is essentially 0 times x1, 1 times x1, 0 times x2, 0 times x3, and 0 times x4. Similarly, A acting on x2 gives me the transpose, so I get this, which is 0 times x1, 0 times x2, 1 times x3, and 0 times x4. Ax3 gives me 0, 1, 0, 0. So this is 0 times x1 plus 1 times x2 plus 0 times x3 plus 0 times x4. And Ax4 is 0, 0, 1, 0, 1. This gives me again 0 times x1, x2, x3, and 1 times x4. So the matrix representation of A with respect to the given basis x, so matrix representation of A with respect to the given basis x is the following. Similarly, let's consider another basis for the matrices. So let's have 1 0 0 0 0 0 0 1 0 1 1 0 and 1 1 0. I'm giving a question to you. Verify if this is a basis. Okay. Now, if let's not label them as x1, x2, y1, y2, y3, y4. So A acting on y1 is what? The transpose operation is this, which is 1 times y1 plus 0 times y2, 0 times y3, and 0 times y4. What is A acting on y2? It is 0 times y1, 1 times y2, 0 times y3 plus 0 times y4. A acting on y3 0 1 1 0, 0 acting on y1, 0 with y2, 0 so not 0, 1 with y3 and 0 with y4. A acting on y4 is 1 0 1 0. Right. So what are the scalars that would come up here? Let's find out what are the scalars. So is 2 times y1, 0 times y2, 1 times y3 and minus 1 times y4. So the matrix representation of A with respect to basis y is let's see, 1 0 0 0 0 1 0 0 0 0 1 0 2 0 1 minus 1. So if you notice, the matrix representation of the transpose operation with respect to basis x and with respect to basis y are different. Okay, so now once we know that what is the uh, matrix representation of A is with respect to a basis x, let's see how we can use this. So if you remember at the start of the discussion, we said that y is a vector that we obtained by A acting on the vector x, where y can be represented as a linear combination of the basis vectors xi belonging to the basis and Similarly, x also is a linear combination of the basis vectors xi. Now please note here, since the basis forms the coordinate frame for the vector space, the scalars associated in the linear combination are the coordinates. So beta 1 till beta n, the coordinates of the vector y with respect to the basis x. Similarly, alpha 1 till alpha n can also be thought of something like coordinates of the vector x with respect to the basis x. Okay. What we are interested in is when A acts on the vector x, it gives you the vector y. So how are these coordinates of vector x and vector y related to each other? So this is where we'll see that the matrix representation of A comes in handy. Okay, so let's see what happens. We saw that y can be expressed as this. Uh, Let us express it in this form. This is more convenient to handle, which I'll write as the basis vectors from x and the coordinate with respect to the basis vector x. Similarly, I can express my vector x with respect to this basis of calligraphic x and the coordinate in this particular basis. So this is what I have. Okay, now y is what? Ax, which is A acting on this, and this is, if you remember how we derived the expression for the matrix representation of A, we essentially had A multiplied with the vectors x1, x2 till xn, and then we arrived on the fact that it is something like a matrix representation. So if you refer back, what you'll see that this is nothing but the basis vector x multiplied by the matrix representation of A with respect to x. Okay, so I can write this as the basis vector x multiplied by A times x and the coordinates alpha x. What was y? Y is essentially in terms of the coordinates beta. So if you compare this with this, if you see this, what you get is the coordinates of y is nothing but matrix multiplication of A multiplied by the coordinates of x. Okay, so this is how the coordinates are related. So for this, let us take up some examples and check how does this or what does this actually mean. So we'll take the derivative operation. Okay, so this is the vector space under consideration. The basis that we'll be considering is the vectors 1 t t square. The linear transform that we are talking of is the derivative operation, which we represented as d, and we saw that this is the matrix representation of the derivative operation with respect to the basis x. So this is what we have. So let's say that you take a polynomial which is 5 plus 7t plus or let's say minus t square. Okay, so what is y that you get when the derivative operator acts on this is nothing but 7 minus 2t. This is what we get. Now so the coordinates here are what? 5, 7, minus 1. The coordinates here are what? 7, minus 2, and 0. Right? So let's see if we can relate these coordinates beta and alpha with the matrix multiplication D, matrix representation D. So the relationship that we got was essentially this. This is 0, 0, 0, 1, 0, 0, 0, 2, 0, and then you have 5, 7, minus 1. Let's see if you multiply this, you get what? You have 7, you have minus 2, you have 0. So this is the coordinates of the vector x. This is the matrix representation of the operator with respect to the basis x. And this is the coordinate that you get from the relationship with respect to the basis x for the vector y. And if you compare it with the operation that we had done, it is exactly the same. Okay. So what is happening is when someone says that a vector is received, a vector is obtained by the operation of a linear transform over another vector. Okay, let's say y is obtained by by the action of a linear transformation A on the vector x. It is same as obtaining the coordinates of y by having a matrix representation of A multiplied to the coordinates of x, where all of them are with the same basis under consideration. So similarly, we think we had discussed for a transpose operation. You can check for the transpose operation as well. Also, definitely do check it for the other basis of this polynomial space, second degree polynomial space. For example, the basis y that we have taken 1t and 1 minus t square. We had a derivative operation represented as matrix representation there, and try to find out what are the coordinates of x with respect to the basis y and the coordinates of vector y with respect to the basis y, and perform this operation and see whether you are able to get that or not. Okay, so this is one use of the matrix representation. Another use of matrix representation is something like this. Consider a vector space V over a field F, let X, this calligraphic X and calligraphic Y, be two bases for the vector space V. Let V be a vector in the vector space. So V in terms of basis X has the coordinates alpha X, and in terms of the basis Y has the coordinates, let's say beta Y. Okay, the same vector in two different coordinate frames has, so how are the coordinates in basis X related to the coordinates in basis Y, where they are coordinates for the same vectors but in different bases, so different coordinate frames. Okay, so let P be a linear transformation such that Pxj, or rather I should say Yj is equal to Pxj, where Yj is from the basis Y and Xj is from the basis X, and this holds true for all j. Okay, so there always exists such a P. Also note that P is an invertible linear transform. I suggest that you prove this. Now, what we have here is Yj or Y to be in this form. Right. How do you get this? This is basically coming from the fact that Yj is Pxj, and this I can always represent as X and the column vector E1j till Enj. Right. So this is coming from here, from this relationship. So this is what we have. Now, so V is what? Basis Y into beta Y. And if we replace Y from upstairs, what we get? Is this. But we also know that V in terms of basis X is this. So if we compare these two, this yields that the coordinates in basis X is obtained by multiplying the matrix representation of P with respect to basis X to the coordinates in basis Y. Okay. So the coordinates in basis x are obtained by multiplying the matrix representation of P with respect to the basis x with the coordinates obtained in basis y. Or similarly, the coordinates in basis y is equal to this. So what you should observe here, that will come to this why I am writing px inverse. So coordinates of v in basis x is equal to matrix representation of P in basis x multiplied by coordinates of v in basis y. Okay, so this is what we have. Now please note that if a linear transformation is invertible, I'll add this here because this is arising here for the first time. If linear transformation is invertible, then the corresponding matrix is also invertible. Okay, so this is something that you should know. Now whatever we did here is essentially known as the change of basis. So what we are trying to see is, if we change from one coordinate frame to another coordinate frame, then how the coordinates get transformed. Okay, so this whatever we saw is also termed as a change of basis. If you go from one coordinate frame to another coordinate frame, how the coordinates from coordinate frame 1 change to the coordinates in coordinate frame 2. Okay, interestingly, okay, we had seen something like a product of linear transforms, right? So let's see be a linear transform, which is a product of two linear transforms. Then the matrix representation of C with respect to basis X is same as the product of the matrix representation of A with respect to basis X with the matrix representation of B with respect to the same basis X. Okay, so I suggest that you try proving this. Okay, now suppose you have a vector space. Consider a vector space V over field F. Let A be a linear transform on the vector field V. Consider the bases X and Y. These bases are not equal to each other. matrix representation of A with respect to basis x and y are ax and ay respectively. Okay, so you have a vector space over a certain field. A is a linear transform defined on the vector space with respect to one basis x. A has a matrix representation Ax with respect to another basis y. A has a matrix representation Ay. What we are interested in here is how are these two related. So when we said that given a matrix, the matrix representation, given a linear transformation, the matrix representation of the linear transformation with respect to the basis is unique. But when the basis changes, the matrix representation might change. So we have, let's say, two different bases and there are corresponding matrix representation of a given linear transform. So how are these two matrix representations related? Okay. So for this, again, we know that given two bases, we have a linear transform that takes you from one basis to another basis. Okay. So let P be a linear transformation such that Yj is Pxj or xj belonging to the basis x and yj belonging to the basis y. This is true for all j from 1 to n. Let's say that we have this. Okay. Now sorry. So when we have this, what is essentially this saying? That basis y is px times x times this. Okay, so we just discussed how this actually comes up. And please also note that P is an invertible transform, and I think I asked you to prove that it's actually invertible transform. So Px is also an invertible matrix. Okay, now let's say that when A acts on the basis vectors of y, what we essentially have is this. Similarly, A acting on the basis vectors of x, we have this. So we have already seen how this has come up. So this is basically where we saw how matrix representation of A can be written as. Okay, we have this. Now, A on Y is also like A on this. Which is what? Which is this. Similarly, A on Y, we saw that we get this is same as this, right? So if you compare these two, this essentially is that this particular relationship holds, which implies that the matrix representation of A in terms of Y is equal to Px inverse Ax Px. Okay, this is known as the similarity transformation. So Ax and Ay essentially represent the same linear transformation, but they are different matrix representations because of different bases under consideration. So the basis matrix representation of A with respect to basis Y is related to the matrix representation of A with respect to the basis X through the linear transformation that relates the basis Y with basis X. And hence we get this expression in the green box, and this is known as the similarity transformation. So the properties of the linear transformations are essentially preserved, it's just that the representations are different. Okay, now sometimes what might happen is this. So consider a vector space V over a field F. Let A and B be two linear transformations on V. Let X and Y be two bases of V. The matrix representation of A with respect to basis X is same as the matrix representation of B with respect to basis Y. How are the two linear transforms related? Okay, so this is the question. So you have a base vector space V over a field F. There are two different linear transforms A and B, and consider two different bases X and Y. So these bases X and Y and the linear transforms A and B are such that matrix representation of A with respect to basis X is same as the matrix representation of B with respect to the basis Y. And now the question is, how is A related to B? Okay, so let's try to find out. So again, we'll say that let there be a linear transform E such that Yj equal to Exj, where Xj belongs to the basis X, Yj belongs to the basis Y, is true for all J. Essentially what we have here is the basis Y is equal to linear transform V acting on the basis X. Now the linear transform V acting on the basis Y is what? Is Y multiplied by the matrix representation of B with respect to the basis Y. Now this is same as X dx by. Now we know that by is same as ax, so I can express this as x ex ax. So this is same as ea acting on x. By can also be expressed as bp acting on x. If we compare these two, what we get is bp to be equal to ea, which implies that the transformation, the linear transformation B is same as P A P inverse. Okay, and this is also known as the similarity transformation. Okay, so this is how the linear transformation operations are related with each other when their matrix representations are same in some basis. Fine. So this essentially is of the last part of this linear transformations is something known as the invariance. Okay, so consider a vector space V over a field F. Let M be a subspace of V. Let A be a linear transformation on the vector space V. The subspace M is said to be invariant with respect to the linear transformation A if for any vector that you take from the subspace, if A acts on the vector, the resulting vector will always go and lie back in the same subspace. So essentially the transformation does not map the vectors out from the subspace. The mapping remains inside the subspace. Okay, so that is when we say that a subspace M is invariant with respect to the linear transformation A. Okay, now let's say that X is a basis of the vector space V with X equal to x1 till xn and xm plus 1 till xn, where xm, which is a collection of the first m basis vectors from the basis X is a basis of the subspace N. Okay. So how is the matrix representation of A with respect to such a basis X? Okay. So X is a basis of the vector space V, where the first m vectors from the basis X form the basis for the subspace N. Now, if you want to find the matrix representation of A with respect to such a X, where M is invariant with respect to the subspace, then how would the structure look like? Okay. So we know that A acting on Xj will give you what? Will give you some vector in the vector space. So you can write it as I equal to 1 to n. A we have been using alpha, so we'll use alpha. Alpha ij xi. Let me purposefully break this sum into two parts. One is I equal to 1 to n alpha ij xi plus I equal to m plus 1 till n alpha ij xi. Now m is invariant with respect to the linear transform A. We'll keep this in mind. When I is from 1 to m, or when j is from 1 to m, Axj will be equal to I equal to 1 to m alpha ij xi plus this. Now since xj belongs to the subspace M and M is invariant with respect to A, the coefficients in this part of the summation will all be 0. So this is same as expressing it like this: alpha ij xi. When j belongs to m plus 1 till n, the two components of the summation remain. Okay, because we are not sure which coefficient will be 0, which is non-zero, and so on. But when j belongs to 1 to m, basically the vectors are being taken from the subspace M, then they cannot be, they will have no components associated with the basis vectors xm plus 1 till xn. So this is what we have. So Ax is this, where the structure of the matrix will be A1x, then the 0 matrix, it may represent as Bx, which is coming from this part, and A2x, which is coming from this part. Okay, so this is how the matrix representation of A will look like. The sizes of this matrix are, this is of the size m cross m, this is of the size n minus m cross n minus m. So basically you can now figure out the sizes of the remaining matrices. Okay, so we'll stop here. Thank you.